welcome. We're now ready to take a look at what is called the sample linear correlation coefficient. So after we go out and collect sample data, we're going to be graphing that data and determining whether or not there appears to be a correlation that is linear. So a straight line pattern that appears to be emerging in the data. So our value R is going to measure both the strength and direction of the correlation. So strength refers to how tightly the values or data points adhere to a pattern, in our case, a straight line. And then direction for us will indicate either a positive or negative association. So let's take a look at some graphs here. So mathematically, this value of R is always going to be a number between -1 and 1. And let me talk about what happens if R is exactly 1. So that would be this graph. If R were exactly a +1, that means that our data values would adhere to a perfectly straight line with a positive slope. On the other extreme, if R were -1, they would still adhere to a perfectly straight line, but now we would have a negative association, so a negative slope. And then in reality, when we collect sample data, we're never going to see the perfectly straight lines. We're trying to measure how closely we are seeing a trend. So generally speaking, if R were 0, that would mean we're not seeing any linear trend. And that would be like this one, not seeing really a pattern at all. The closer that R gets to 1, the more we're seeing a pattern emerge. And in this case, let's take a look at this picture. So R is 0.86. So I am seeing some adherence to a positively sloped line. It's not perfect, but the closer that R it gets to a +1, the more we're seeing that adherence to a straight line. And then on the other end, as R gets close to -1, we're starting to see adherence to that pattern, but it's going to be that negative slope. Now, I'll just mention here that you can have patterns like this one. It would be called curvilinear. And the value for R there would still be 0 because this is not going to measure, R is not measuring anything other than linear correlation. So we won't be studying curvilinear in this class. We're going to be looking to investigate whether or not we're seeing evidence of a positive linear relationship or a negative linear relationship. And again, we're going to be basing our conclusions on our populations based on taking sample data. So the sample linear correlation coefficient, we often just say correlation coefficient. So for the sample, it's a lowercase r. And we're going to try to use R to draw a conclusion about the population. And the population linear correlation coefficient is our next Greek letter of the alphabet. That is a Greek rho. Our HO is rho. So we are not going to do a hypothesis test yet, but eventually we will. And we'll see if the sample correlation coefficient provides us enough evidence to draw a conclusion about the population when it comes to a linear correlation between our two variables. Okay, so before we get into that, let's do an example. All right, so it says, a researcher is interested in whether the number of surfers at a particular beach is related to the wave height. So do more surfers show up with big waves, or is there no association or relationship? And to investigate, we'll need to get some data. So she considers a random sample of 7 days and keeps track of that data. And we're going to find the correlation coefficient for the sample, lowercase r, by running it's called a linear regression t-test. So linear for straight line pattern, we're investigating. Regression, we'll get to that in a bit, and then t-test. All right, so your first step is to enter the data in the calculator. So stat edit, and I've gone ahead and entered that data. So if you wanted to pause the video and get your wave heights in list 1, and the number of surfers that showed up in list 2. All right. So now that we have the data in, I'm going to go ahead and do some graphing by hand here so that we have an image. So let's go ahead and label our x-axis here. So x, we're keeping track of the wave height on a particular day. This was in feet. And then my y-axis represents the number of surfers that show up on that particular day for that wave height. And then I've gone ahead and established a scale for us. So we're going to go up by 10 on the y-axis. And then on the x-axis, we can go up by 1. You won't have to worry about setting a scale. I will always take care of that. And then let's graph these ordered pairs. So there was a day with a 3-foot wave height and 24 surfers showed up. So this does not need to be perfect. We are just trying to get an idea here. So there's my 324. And then wave height 1, we had 15 surfers show up. So I'm just going to keep up that process here. And then wave height 5, we had 55. And then wave height 4, 45. Another day with a wave height of 1 and 8 surfers showed up that day. And then 4-foot wave height, that day we had 50 surfers show up. And then finally 6-foot waves, we had 62 surfers show up. All right, so even just based on those 7 days, it does appear there could be a positive correlation between these. So it does appear that as wave heights get bigger, the number of surfers showing up tend to get bigger. We will be conducting a hypothesis test in order to really draw a conclusion based on this evidence later. For now, we just want to focus on finding R. So to run our linear regression t-test, you're going to hit your stat button and go to tests. And linear regression is towards the bottom, so I usually scroll up just to get there faster. So you're looking for linear regression t-test. And then we put our x values in L1, our y values in L2. So you want to make sure it says that. Frequency is always 1. And then eventually here, when we conduct a hypothesis test, it will always be a two-tailed test. So it's going to be a not equal to 0. And you'll see that Greek row there for the population. So we'll always be testing claims about the entire population based on the sample data. Regression equation, you can leave empty. And we'll just do calculate. All right, so a lot of information provided there, but if you scroll down, the last entry there will be R. And we're going to round that to 3 places, so 0.971. So that is getting close to +1. So remember, the closer, I'm going to scroll up just for a moment, the closer that R gets to 1, the more evidence we're seeing of a positive correlation. And again, we'll conduct a hypothesis test later to decide if that is a significant value. All right, but before we do that, I want to look at, for this particular sample, what was the mean for the 7 days in terms of wave height, and what was the mean number of surfers for this data. So I'm going to come back to my calculator and hit stat, calculate. And instead of 1 bar stats, we're going to pick 2 bar stats. So our calculator can work with 2 variables, but we do need to tell the calculator that we'd like it to look in L1 and L2 for our X and Y value. And I'll hit enter. And then I can see at the top, I did have to round that. My sample wave height, sample mean wave height was 3.4 feet. And there's my Y bar. Sample number of surfers was 37. Okay, so what we're going to do on the graph here, I'm going to just switch colors for a moment. What we're going to do on the graph is look for our X bar 3.4. Again, this doesn't have to be perfect, but that was the mean of the wave heights. And what I'm going to do is draw a line through that value. And sorry, my line is certainly not perfectly straight, but hopefully you get the idea. And then my average number of surfers for that sample, so my Y bar came out to be 37. So I'm going to draw a horizontal line there. All right. So what happens with a positive correlation is that those two values create basically a coordinate system. So this was my X bar value and my Y bar value. So if we have a positive correlation, there's going to be a tendency for the data to be in this quadrant and this one. So if you remember your quadrants, that is quadrant 1 and 3. So here, the data will tend to be in those quadrants if we see a positive correlation. So these questions that will ask us about pairing tendency. So let's look at this statement. For this data, if we look at number of surfers that were less than the mean, so let me just label where that would be on the graph. So number of surfers less than the mean. This was the mean number of surfers. So these surfers, those values would be less than the mean. So these are less than the mean number of surfers. So if we look at those Y values, the data is not here. The data all tends to be here. It doesn't have to be perfect 100% of the data, but there's going to be the tendency for the data to be here. And if this is the sample mean wave height, then this data corresponds to wave heights that are less than the mean wave height. So what they're getting at here is this tendency. So if you have numbers of surfers that are below average, they tend to be paired with wave heights that are also below average. So wave heights that are less than the mean or the wave heights. So I call this same pairing. If one value is less than the mean, it tends to be paired with the other data value also being less than the mean. And as well, so for the data, if we look at number of surfers greater than the mean, so number of surfers greater than the mean would be here. And that data shows up in this quadrant. And so that corresponds to wave heights that are also greater than the mean. So for this data, surfers that are greater than the mean tend to be paired with wave heights that are greater than the mean. All right. So that is how we address pairing. And then our next step is to decide if this evidence really is strong enough, if this value for R is close enough to 1 to lead us to conclude that this relationship is true for an entire population of data. So not just this particular 7 days of data, but can we draw this conclusion about wave heights being related to number of surfers for the entire population?